The Doppler effect or Doppler shift describes the apparent change in frequency of a wave caused by relative motion between the source of the wave and the observer. Waves emitted by an object traveling toward an observer get compressed, prompting a higher frequency as the source approaches the observer. In contrast, waves emitted by a source traveling away from the observer get stretched out, prompting a lower frequency. The Doppler effect is used to measure the speed at which stars and galaxies are approaching or receding from us, in a mechanism named redshift or blueshift. Redshift happens when an object moves away from us. The light is shifted to the red end of the spectrum as its wavelengths get stronger. Blueshift happens when an object moves closer. The light moves to the blue end of the spectrum as its wavelengths get shorter. The redshift of an object is measured by examining the absorption or emission lines in its spectrum. These lines are unique for each element and always have the same spacing. When an object in space moves towards or away from us, the lines can be found at different wavelengths than where they would be if an object were not moving. Subtle changes in the color of starlight let astronomers find planets, measure the speeds of galaxies, and track the expansion of the universe. Astronomers used redshifts to track the rotation of our galaxy, tease out the subtle tug of a distant planet on its parent star, and measure the expansion rate of distant galaxies and this universe. Further the spectral line shifts towards the red end of the spectra, the faster the galaxy is moving from us. In 1929, astronomer Edwin Hubble matched up these redshifts with distance estimates to these galaxies and found that most galaxies displayed a redshift that led to the conclusion that the galaxies are moving away from the Earth at a fast rate and that the universe must be expanding. A red shift in light indicates that the object is moving away from the observer. Blue light has waves that are closer together and red light has waves that are further apart. The logic is that if the universe is observed to be moving apart, it must have been closer together in the past. The Big Bang theory is that the universe is moving apart from a central point that once existed. The redshift indicates that the universe is expanding outward at an ever-increasing rate of expansion, supporting the idea of the Big Bang theory. As the universe expands, the galaxies will get further from each other, and the apparent velocity will appear to be larger for the more distant galaxies. American astronomer Edwin Hubble was the first to describe the redshift phenomenon and tie it to an expanding universe. His observations, revealed in 1929, show that nearly all galaxies he observed are moving away. Hence, the further a galaxy, the faster it is receding from Earth. The speed of light is 299,792,458 meters per second. According to Einstein's theory of relativity, nothing is faster than the speed of light. The distance for light to travel in 1 year is approximately 4 trillion miles. So if you were in a spaceship moving at 50,000 miles per hour, it would take you about 40,000 years to travel 1 light year. When we look at stars and galaxies, it is considered that we're looking back in time. This is because of the infinite speed of light. When we look at objects that are very far distances away from us, the light that is hitting us now will have started from the object quite a long time ago. So in effect, we aren't looking at what the object looks like now, but what it looked like some time ago. There are many universal distances for measurements. An astronomical unit is an average speed between the Earth and the Sun, which is about 93 million miles or 150 million kilometers. Astronomical units are usually used to measure the distance within our solar system. A parsec is defined as the distance at which one astronomical unit subtends an angle of 1 arc second, which corresponds to 648,000 pi astronomical units. 1 parsec is equal to about 3.26 light years in length. In 1965, Arno A. Penzias and Robert W. Wilson of Bell Laboratories were testing a sensitive horn antenna which was designed for detecting low levels of microwave radiation. They found that a group of astronomers had predicted that there would be a residual microwave background radiation left over from the Big Bang and were planning an experiment to try and detect it. Penzias and Wilson were awarded the Nobel Prize in 1978 for the discovery. The cosmic background radiation is a radiation that tells us the age and composition of the universe. The cosmic microwave background is the oldest light in the universe, dating from the first epoch in which protons could travel freely. Big Bang theory predicts that the early universe was a very hot place and that as it expands, the gas within it cools. Thus, the universe should be filled with radiation that is literally the remnant heat left over from the Big Bang. The universe was born with the Big Bang as an unimaginably hot, dense point. It experienced an incredible burst of expansion known as inflation, in which space itself expanded faster than the speed of light. Although the expansion of the universe gradually slowed down as the matter in the universe pulled on itself via gravity, about 5 or 6 billion years after the Big Bang, a mysterious force now called dark energy began speeding up the expansion of the universe again, a phenomenon that continues today. 9 billion years, the universe expanded at an increasingly fast rate, and the universe has cooled down tremendously, proving the theory that the universe expands as it cools, referring back to prove that the expanding universe is evidence of the Big Bang theory. The universe is currently estimated at roughly 13.8 billion years old, give or take 130 million years. This estimate came from measuring the composition of matter and the energy density in the universe. Scientists today are fairly confident that the Milky Way is probably between 100,000 and 150,000 light years across. The observable universe is of course much larger. According to the current thinking, it is about 93 billion light years in diameter. Observations suggest that the expansion of the universe will continue forever. If so, then a popular theory is that the universe will cool as it expands, eventually becoming too cold to sustain life.